I hope everybody is fine and I am able to share uh, whatever I can. And in this video, I'll be talking about the probability current density. And if I rightly talk about the wave function is to be interpreted by the probability amplitudes. So that's the that's the essentiality of the wave function, that we have to interpret this wave function in terms of probabilities or probability amplitudes, and the motion of the particle is clearly to be associated with the motion of the wave packet. So here we have motion of wave packet. Now, this general idea can be quantitatively understood in calculating the introduction of something like probability current density. Probability current density, that's out there on the title. Now, if I assume that probability density that we define as PR is the probability density, and how do we define it? If I have to calculate it over a volume V, I'll define it as, oh, shit. So it will be defined as P of R d tau. And for this PR, if I have a wave function psi, then certainly it has to go like integral over V, then psi star d tau. So this thing is the probability. I mean, here I'm trying. What am I trying is that this the probability of finding the particle at some particular point in the space that's given by P of R, and and what sense it makes here is that I want to ensure that the probability of finding this particle in some volume, which is bound by some surface. There's some volume which is bound by some surface, and that probability can be written as P of R is integral psi star d tau. And when I have to incorporate the flux that I am talking about, then we understand that this d tau is the volume element as dx, dy, and dz. And to go with this, in order to have the flow, of these probabilities, what we are trying to imagine here is the flow of these probabilities, right? And as we have classical flows like flow of a liquid or flow of electrons, but here we are talking about flow of these probabilities that are invoked in understanding the various properties of these wave packets. So what should I do is that I should write down the rate of this probability as dp by dt. So if this thing goes well, so I should take t by dt of psi star d tau. That should be the case. And here we can think of using UV rule. So psi will remain as it's. I have the integral. It's a volume integral. So then I'll have d psi star by dt plus psi star as it's, then d psi upon dt. Now this whole thing is enclosed by t tau. So in the left hand side, I have the rate of change of these probabilities that I'm trying to imagine. And to move on from here, let me call this, say, equation 1 for the time being. Let me write down the Schrodinger's time-dependent equation for psi. So what's that? That's minus h cross square by 2m del square psi plus v of psi is equal to I h cross dou psi by dou t. Now let's take the complex conjugate of Schrodinger's equation. So what we'll have is, so taking complex conjugate. Okay, so what I'll have is minus h cross square by 2m del square psi. So now psi is going to change into psi star plus v psi star is equal to, so this is going to change to negative I h cross dou psi star by dou t. Now, I would like to call this equation as equation 2, and I would like to call this equation as equation 3. Now, what should I do is I would like to multiply this equation 2 that I have here by psi star. So if I multiply this equation by psi star, I will have psi star here, and I will have psi star here, and I will have psi star here. And the same thing I would like to do with this equation, but in this case, I'm gonna multiply this this equation by psi. So here I will have psi, here I will have psi, and here I will have psi. Okay, it's looking a bit crazy, but this is the right way to do it right now. So after this, what I would like to do is I would like to subtract 2 and 3. And on subtraction, we can see this v psi star psi. V psi psi star is going to die. It will not remain there in the original equation. So I have not even numbered it. So subtracting. So I should say subtracting 2 and 3. Okay, so what we are going to come up with is we will have h cross square by 2m. Yeah, what we will have is psi star del 2 psi, then minus psi del 2 psi star. Yeah, bracket closed, minus I h cross. Yeah, then psi dou psi star by dou t plus psi star dou psi by dou t. This should be the result. This should be the result of the subtraction, and the potential energy term is going to it's going to die because one of them will be negative, and we have the situation here, and I would like to have the transformation of these. Let's make it a symmetrical kind of equation. So this will imply, okay, let me go with psi dou psi star by dou t plus psi star dou psi by dou t. Yeah, this must be equal to, so you have to get it down. Iota is coming down. So what we will have is minus h cross by 2mi, okay, times psi star del square psi minus psi del square psi star. So this is the equation that that I have arrived at, and I think this term is already defined somewhere. Yeah, it is defined. This term is defined. Okay, let's move on. Where are we right now? So this term is psi. Where is the first page? Yeah, that's it. So this term is, yeah. Okay, I have psi d psi star by dt plus psi star d psi by dt. Okay, so this thing is psi dou psi star by dou t plus psi star dou psi by dou t. Now we can use for this dp by dt that we have already defined in terms of that. So moving on from here is for this, am I going to write dp by dt is equal to minus h cross by twice mi times psi star, okay, psi star, then del 2 psi minus psi del 2 psi star, and that's it. Now, if I take I have to take the integral of this, so this will be integral over the volume dv. That's how we define it, and I can immediately think of using Green's theorem here, and what Green's theorem does is it converts the volume integral into the area integral, right? So using Green's theorem here in this equation, what am I going to get is dp by dt is minus h cross by 2mi. So integral here, this was volume integral, it's going to change into area integral. So for that, say I will write s. Okay, then what's going to happen here is understood. We'll have psi star del psi minus psi del psi star and ds. So this is going to be the result. And let me assume that here, let me define a vector here again. Suppose I have a vector, say x, vector s, okay, which is a function of r and time, and this vector I define as minus h cross by 2mi times psi star del psi minus psi del psi star ds. Oh, sorry, there's no ds. I will be using this s of rt in this integral. So what I will come up with is dp by dt, the rate of change of those probabilities that are linked with those wave packets that we have can be written as the minus integral of s dot dA, right? Where s is a vector defined by this quantity in the right hand side. So this is in terms of it's an integral over the area, and we can immediately convert this integral using divergence theorem into the divergence of s. So we can write down, so using that divergence theorem, we can obtain dp by dt is minus divergence of this s. Okay, so what we did is we have used Gauss divergence theorem, and we got the result. Now what we have is it is something that we have seen the like of in classical mechanics, del dot s, this is equal to 0. Okay, so This equation is it's very much analogous to the well-known equation that we have from hydrodynamics. And what we have there is del rho by del T plus divergence of some J equals 0. Okay, so this is analogous to this, and where this rho in this case is basically the fluid density. It's the density of the fluid, and J is the current density. And the simple interpretation that we can have here of this equation is that the changes in the fluid density can be regarded as some unbalanced flow of this current across the boundaries. So when you have the unbalanced flow of the current, that's going to give the changes in the density of the fluid. Now it is quite reasonable to interpret the vector S that we have chosen here as the probability current density. This S can be chosen as probability current density. And so that from this equation, when I choose this as the probability current density, so from this equation, we may interpret the changes the changes in the probability they are due to the flow of the probability current, whatever the case may be. And we can make use of the relevant operators to evaluate the equation. So that should be clear. So this is analogous, and this is the equation of continuity in the domain of probabilities that are linked with the wave packet.